In early January 1916, San Diego County looked exactly as it was designed to appear: controlled, dry, and predictable. The riverbeds that traced the coastal valleys held only scattered pools of standing water, remnants of modest winter rain. Dust settled on the native chaparral covering the steep slopes of the Laguna Mountains and the Cuyamaca Range. Along the floor of the Ate Valley, 20 miles south of San Diego, the lower Ate Dam stood 40 feet high and 800 feet across, holding back a reservoir that represented the triumph of modern water management over an arid landscape. Southern California's water philosophy in 1916 rested on a simple premise: capture every drop, store it behind concrete and earth, and distribute it according to human need rather than natural flow. The region's rivers were short and seasonal, draining narrow watersheds that dropped quickly from mountain headwaters to the Pacific. The Sweetwater River, the Ate River, the San Diego River, all of them ran vigorously during wet winters and vanished entirely by summer. Engineers responded by building dams across their channels, creating reservoirs that turned erratic flow into steady supply. The infrastructure was new. Most of the major dams had been completed within the previous 15 years. The landscape suggested permanence. Rail lines crossed the valleys on low embankments, their grades calculated for minimal elevation change. The San Diego and Arizona Railway pushed eastward through Carrizo Gorge, cutting through solid rock where the mountains pressed close to the desert. Telegraph lines followed the rail corridors, connecting San Diego to the interior and to the national network beyond. Roads wound through the valleys, unpaved but serviceable, linking ranches and small towns to the growing city on the coast. The reservoirs sat quietly behind their dams. The lower Ate Reservoir held water for the city of San Diego. The Sweetwater Dam, completed in 1888 and one of the tallest masonry dams in the United States, impounded a reservoir that served the southern county. Morna Dam, high in the backcountry near the Mexican border, stored water from the upper Cottonwood Creek drainage. Each structure represented confidence in the capacity of engineering to impose order on a difficult hydrology. January brought the expectation of rain, but not concern. The region's climate was Mediterranean: wet winters, dry summers, and annual totals that rarely exceeded 10 inches. The infrastructure had been designed with that rhythm in mind. Spillways were built to handle seasonal overflow. Channels were maintained to convey typical storm runoff. The dams themselves were sized for the floods that historical records suggested might occur once every few decades. There was no reason, in early January, to believe the system would fail. The reservoirs were filling normally. The dams showed no signs of distress. The valleys remained dry except where water was intentionally released for irrigation or municipal use. Southern California had learned to manage scarcity. It had not yet learned what happened when scarcity ended. The meteorological pattern that settled over Southern California in mid-January 1916 was neither violent nor brief. A series of Pacific storm systems moved onshore in succession, each one carrying moisture from the subtropical latitudes and stalling against the coastal mountains. The storms did not arrive as dramatic events. They arrived as continuous weather, persistent and unrelenting, dropping rain over the same watersheds day after day. The rain began on January 10th. By January 15th, weather stations across San Diego County were recording totals that exceeded normal monthly averages. By January 20th, those totals had doubled. The National Weather Service station at San Diego measured more than 6 inches in 10 days. In the mountains, where orographic lifting forced air masses upward and wrung additional moisture from them, totals climbed past 15 inches. Morna Dam, at an elevation of 3,000 feet, recorded over 20 inches before its rain gauge overflowed. The rainfall did not distribute evenly. The western slopes of the Laguna and Cuyamaca Mountains received the heaviest precipitation, as prevailing winds pushed moisture-laden air upward into cooler elevations. The interior valleys, sheltered slightly by topography, received less, but still far more than the soil and vegetation could absorb. The region's hydrology was adapted to scarcity. Root systems were shallow. Soil layers were thin, underlain by bedrock or hardpan. When rain fell in typical amounts, the ground absorbed it slowly, releasing it gradually into springs and seeps. When rain fell continuously, the ground saturated quickly and refused additional input. Runoff began almost immediately. Water sheeted across slopes, converging into gullies and ravines that swelled into torrents. The short, steep rivers that drained the coastal ranges responded within hours. Stream gauges recorded flows that climbed from cubic feet per second to thousands of cubic feet per second. The Sweetwater River, normally a trickle in January, became a roaring channel 30 feet wide. The San Diego River, which often went dry by midsummer, carried floodwaters westward toward Mission Valley and the Bay. The infrastructure designed to control this hydrology had been calibrated for different conditions. Dams and reservoirs assumed seasonal rain followed by months of drought. Spillways were sized for peak flows derived from historical data that spanned only a few decades. The assumption underlying every calculation was that extreme rainfall in this region would be brief, measured in hours or days, not weeks. The storms of January 1916 invalidated that assumption without drama or warning. They simply continued. By January 25th, every reservoir in San Diego County was full. Water flowed over spillways that had been designed for occasional use. The Lower Ate Reservoir, impounded by an earthen dam with a concrete core, rose to within inches of its crest. Sweetwater Reservoir filled and began releasing water at rates that exceeded the capacity of the downstream channel. Morna Reservoir, isolated in the mountains, overtopped its spillway and sent water cascading down Cottonwood Creek toward Barrett Dam and the valleys beyond. The soil across the region had reached saturation. Additional rainfall became immediate runoff. The streams feeding the reservoirs were no longer conveying typical storm flows. They were conveying the accumulated precipitation from entire watersheds, compressed into channels never designed to carry such volumes. The dams, built to store water, were now being asked to pass it. The spillways, built to bleed off excess during brief flood events, were running continuously at maximum capacity. The system was not failing yet. It was simply running out of margin. By the morning of January 27, 1916, the Lower Ate Dam was holding back a reservoir that had risen to its maximum design elevation. Water poured over the spillway in a continuous sheet, white with aeration, loud enough to be heard a mile downstream. The dam itself was an earthen structure, 40 feet high at its tallest point, reinforced internally with a concrete core wall designed to prevent seepage. The upstream face was protected by riprap. The downstream face sloped gently toward the valley floor, planted with vegetation intended to prevent erosion. The spillway was cut into the natural hillside at the eastern end of the dam, a channel designed to carry overflow around the structure and back into the Ate River below. It had been sized for the largest flood anyone could imagine in 1897, when the dam was completed. That flood had been based on rainfall records spanning fewer than 20 years. The water now flowing through the spillway exceeded those calculations. It had been flowing continuously for more than 48 hours. Water pressure against the upstream face of the dam was immense. The reservoir held millions of gallons, all of it pressing outward, seeking any weakness in the structure. Earthen dams depend on mass and impermeability. The core wall prevents water from moving through the dam. The earthen embankment on either side provides weight and stability. If water finds a path through the core, it begins to erode the fill material from the inside. The process is called piping. It starts invisibly, deep within the structure and accelerates exponentially. At approximately 5:00 p.m. on January 27th, a section of the Lower Ate Dam failed. Witnesses downstream reported hearing a sound like sustained thunder. The failure began near the base of the dam, where water pressure was greatest. A section of the concrete core gave way, allowing water to penetrate the earthen fill. Within minutes, the breach widened as water scoured away tons of soil and rock. The dam did not collapse all at once. It eroded progressively, the breach expanding until it was more than 100 feet wide. The reservoir drained rapidly. Water that had been held behind the dam surged into the Ate Valley as a wave estimated at 30 feet high near the breach, diminishing in height but not in volume as it spread downstream. The wave carried debris, pieces of the dam itself, trees stripped from the banks, structures that had stood in the valley for decades. The sound was reported as far as San Diego, a low rumble that persisted for nearly an hour. Upstream, other dams were under similar strain. Sweetwater Dam, a curved masonry structure considered one of the most advanced designs in the American West, held firm, but continued to release water at rates that overwhelmed the downstream channel. The spillway ran at maximum capacity. Water spilled over secondary outlets cut into the hillside as emergency overflows. The dam did not fail, but the valley below flooded as the Sweetwater River carried more water than it had ever been asked to convey. Morna Dam, high in the mountains, was overtopping. Water flowed across its crest, a condition the structure had not been designed to tolerate. The dam held, but only because it was built of masonry rather than earth. Water poured down the downstream face, eroding the toe of the dam and the channel immediately below. Barrett Dam, downstream from Morna, received the combined runoff of the upper watershed and struggled to pass it without failing. Spillways ran continuously. Reservoir levels fluctuated wildly as inflow exceeded outflow. The rain did not stop. On January 28th, additional storms moved onshore. Rivers that had begun to recede surged again. Reservoirs that had dropped slightly after the lower Ate failure refilled within hours. The dams that remained intact were holding, but only barely. The infrastructure designed to capture and control water was being tested beyond its limits, and the limits were moving. The Ate Valley, in the hours after the lower Ate Dam failed, became a channel for water that had been stored for years. The flood wave moved westward toward San Diego Bay, carrying everything the valley had contained. Homes disappeared. Barns folded and were swept downstream. Rail lines that had crossed the valley on low embankments were undercut and washed away. The ties and rails left twisted in the mud miles from their original alignment. The valley floor, normally dry except for the narrow channel of the Ate River, filled wall to wall. Water spread across fields, orchards, and pasture land, moving at speeds measured in miles per hour. The flood was not a single wave but a sustained flow, fed by the emptying reservoir upstream and by continued runoff from the surrounding mountains. The valley had no capacity to absorb or slow the water. It simply conveyed it toward the bay. To the north, the San Diego River was carrying floodwaters from its entire watershed. The river drained the western slope of the Cuyamaca Mountains, gathering flow from dozens of tributaries that descended through steep canyons. In a typical year, the river delivered modest flows to Mission Valley and the tidal estuary at the bay. In January 1916, it delivered a flood that filled the valley from bluff to bluff. The river abandoned its normal channel and spread across the floodplain, submerging farms, rail lines, and the small communities that had grown along its banks. Mission Valley became a temporary lake. Water backed up behind the narrow passage where the river cut through coastal mesas on its way to the bay. The flood moved slowly here, ponding rather than rushing, but the volume was immense. Structures built on the valley floor were inundated. Rail bridges designed for the river's typical winter flow were submerged or destroyed. The valley would remain flooded for days, even after the rain stopped. The Sweetwater River, swollen by continuous releases from Sweetwater Dam, carved new channels through the valley downstream. The normal river corridor, defined by low banks and scattered vegetation, could not contain the flow. Water spread outward, seeking the lowest ground, cutting new paths wherever the terrain allowed. Roads that crossed the valley were washed out. Wooden bridges collapsed when floodwaters undercut their supports. The landscape was being rewritten in real time. In the backcountry, smaller drainages that rarely flowed at all became torrents. Cottonwood Creek, fed by the overflow from Morna Reservoir, carried water at velocities that stripped soil from the banks and moved boulders the size of vehicles. Pine Valley Creek, the Tijuana River, Campo Creek, all of them were running at record levels, cutting into valley floors and widening their channels. The floods were not isolated events. They were the cumulative response of an entire region's hydrology to rainfall it had no capacity to manage. Transportation infrastructure across the county was severed. The San Diego and Arizona Railway, which had taken years to build through the rugged terrain east of the city, was cut in multiple locations. Embankments washed out. Trestles collapsed. Sections of track were left suspended in midair where the ground beneath them had eroded away. The line would remain closed for months. By January 29th, the valleys were rivers. The rivers were unrecognizable. The landscape, shaped by thousands of years of dry cycles interrupted by occasional rain, was being reshaped by a single storm system that refused to move on. By January 30th, 1916, San Diego County was effectively isolated from the rest of California and the nation. The rail lines that connected the region to Los Angeles, to the agricultural interior, and to the transcontinental network had been severed in multiple locations. The San Diego and Arizona Railway, the county's primary link to the east, was impassable. The coastal rail corridor, north toward Los Angeles, had been damaged by flooding along the San Luis Rey River and other drainages. No trains were moving in or out. The isolation was not merely inconvenient, it was logistical. San Diego in 1916 depended on rail transport for nearly everything that sustained a modern city: food, fuel, building materials, mail, manufactured goods. The city's port could receive some supplies by sea, but the volume was insufficient to replace what had moved by rail. Shortages began within days. Prices rose. Goods that had been abundant became scarce. Telegraph lines, which followed the rail corridors, were down across the region. Poles had been toppled by floodwaters or undermined by erosion. Wires sagged into the mud or were swept away entirely. Communication with the outside world was reduced to whatever could be transmitted by coastal cable or by messages carried aboard ships. The county could not reliably report conditions to state or federal authorities. Requests for assistance were delayed or lost. News of the disaster reached the rest of California slowly, filtered through second-hand accounts and incomplete reports. Roads, never robust in a region where rail was the primary means of long-distance travel, were destroyed. The few highways that crossed the coastal ranges or connected towns within the county had been built along valley floors or across low saddles in the ridges. Floods had washed out bridges, undercut roadbeds, and filled sections of road with debris. Travel between towns became difficult or impossible. Rural communities, already remote, were cut off entirely. The disruption extended beyond physical infrastructure. The flood had severed the networks that allowed the region to function as a system. Ranchers could not move livestock to market. Farmers could not ship produce. Businesses dependent on supplies from outside the county could not restock. Workers could not reach job sites. The economy, which had been growing steadily in the years before 1916, stalled. Emergency response was limited by the same constraints. The county had no unified disaster management system. Fire departments, law enforcement, and medical services were local and under-resourced. Mutual aid from neighboring counties was impossible while transportation links remained cut. Communities affected by the flood were left to manage the immediate aftermath on their own, with whatever resources they had on hand. Efforts to restore rail service began as soon as the water receded enough to assess the damage. Crews from the San Diego and Arizona Railway worked eastward from the city, repairing track, rebuilding embankments, and replacing washed-out trestles. Progress was slow. Some sections of the line required complete reconstruction. The most difficult terrain, through Carrizo Gorge, had been damaged in dozens of locations. Repairs would take months, and in some cases, the route had to be relocated entirely. The coastal line north toward Los Angeles was restored more quickly, but only because it had suffered less severe damage. Even so, service remained intermittent for weeks. Temporary repairs allowed limited traffic, but full restoration required engineering work that could not be completed while the ground remained saturated and unstable. By mid-February, the isolation was easing. Telegraph communication was restored along the coastal corridor. Some roads reopened, though many remained impassable. Rail service resumed on a limited schedule. But the damage was done. San Diego County had learned what it meant to be disconnected, and the lesson was not abstract. It was measured in empty shelves, delayed mail, and a local economy forced to contract while the rest of the state moved on. The rain stopped in early February. The storms that had lingered over Southern California for 3 weeks moved eastward into Arizona and dissipated. The reservoirs, which had overflowed for days, began to drop as inflow returned to normal. The rivers, which had filled the valleys, receded into their channels. The floodwater drained westward toward the bay and the ocean, leaving behind a landscape that no longer resembled what it had been. The Ate Valley was filled with mud. The flood had deposited sediment across the valley floor, in some places to a depth of several feet. Debris was scattered everywhere: timbers from destroyed structures, household goods, agricultural equipment, dead livestock. The rail line that had crossed the valley was gone, its embankment eroded, and its tracks twisted into shapes that made them unrecognizable. The site of the lower Ate Dam was a wide breach in the hillside, the reservoir behind it empty, the dam itself reduced to a remnant of earth and broken concrete on either side of the gap. Mission Valley, when the water finally withdrew, revealed the same pattern of destruction. Mud coated everything. Buildings that had survived the flood were damaged beyond use, their foundations undermined, their walls cracked and tilted. The rail bridges across the San Diego River were gone. The valley's agricultural land, which had been productive and valuable, was buried under silt or scoured down to bedrock where the flow had been fastest. The recovery, when it came, would require excavation, reconstruction, and years of work. The economic losses were immediate and measurable. The agricultural sector, which had supplied much of the county's produce, grain, and livestock, was devastated. Orchards had been uprooted. Fields were unplantable. Barns, equipment, and stored crops were destroyed. Ranchers had lost cattle, horses, and sheep, drowned in the floods or swept away. The total agricultural loss was estimated at more than $2 million, a figure that represented years of investment and labor. Infrastructure losses exceeded that total by a substantial margin. The San Diego and Arizona Railway alone reported damages approaching $4 million. The costs included destroyed track, collapsed trestles, washed-out embankments, and the expense of months of repair work. Other rail lines, roads, bridges, telegraph systems, and water delivery infrastructure added millions more. The lower Ate Dam, which had cost approximately $150,000 to build in 1897, was a total loss. Its reconstruction would cost more and take years. The human toll was lower than the infrastructure and economic losses, but it was real. At least 20 people died in the flood, most of them in the Ate Valley when the dam failed. Others died in the backcountry, caught by rising water in remote canyons or swept away while trying to cross swollen streams. The death toll was difficult to verify. Some bodies were never recovered. Some victims were transient workers or immigrants whose presence in the region had not been officially recorded. The final count was likely higher than reported. The flood exposed assumptions that had guided development in Southern California for decades. Dams had been built with confidence that they could contain any flood the region might produce. The lower Ate Dam, and the near failures of others, demonstrated that confidence was misplaced. Rail lines had been routed through valleys because the terrain made construction easier and cheaper. The flood demonstrated that valleys were floodplains, and floodplains were not stable routes. Roads, bridges, and telegraph lines had been placed where they were convenient, not where they were safe. The landscape itself had changed. River channels had widened and deepened. Some tributaries had cut new courses entirely. The sediment deposited in the valleys had raised the elevation of some floodplains and buried others. The infrastructure that survived the flood was now situated in a different geography than the one it had been designed for. Recovery began in February, but it was slow and uneven. The region's economy had contracted. Tax revenues had declined. Federal assistance was limited and slow to arrive. The work of rebuilding fell largely to local governments, private companies, and individual property owners, all of them operating with diminished resources in a landscape that no longer cooperated. The Great Flood of 1916 forced Southern California to reconsider what it thought it knew about water. The region's hydrology had been understood through the lens of scarcity. Engineers had designed dams, reservoirs, and water distribution systems to capture and store every drop that fell during brief winter rains, releasing it carefully through the long dry months. The assumption had been that water was the limiting resource and that controlling it meant preventing waste. The flood demonstrated that water could also arrive as a surplus, and that surplus could destroy infrastructure built on the assumption of scarcity. Dam design changed first. The failure of the Lower Ade Dam was studied extensively by engineers across the state and the nation. The investigation revealed that the dam spillway had been undersized for the flood it encountered, and that the earthen embankment had been vulnerable to internal erosion once water pressure exceeded certain thresholds. The lessons were specific. Spillways needed to be larger, designed for floods that exceeded historical records by substantial margins. Earthen dams needed more robust core walls, better drainage, and more conservative estimates of the loads they might face. The state of California began requiring more rigorous review of dam designs, and existing dams were reevaluated for their capacity to withstand extreme events. Flood control, as a distinct branch of water management, emerged from the disaster. Before 1916, flood control in Southern California had been incidental, a secondary consideration in systems designed primarily for storage and delivery. After 1916, it became central. Engineers began designing channels, levees, and detention basins specifically to convey or temporarily hold floodwater, separate from the infrastructure meant to supply cities and farms. The Los Angeles River, the San Gabriel River, and other drainages across the region were eventually channelized, their flows confined and directed to reduce the risk of catastrophic flooding. The work took decades, but the principle was established in the years immediately following the flood. Watershed planning became more sophisticated. The flood had demonstrated that dams and reservoirs were only part of the system. The entire watershed, the slopes, the soil, the vegetation, the tributary channels, determined how water moved during storms. Engineers began studying watersheds as integrated systems, mapping drainage patterns, measuring runoff coefficients, and modeling how changes in one part of the system affected others. The goal was predictability, understanding how much water would arrive, how fast it would move, and where it would go. Land use policy began to reflect flood risk, though slowly and unevenly. The valleys that had flooded in 1916 were recognized as floodplains, and development in those areas was approached with more caution. Some areas were left undeveloped. Others were built on with the understanding that periodic flooding was possible, and structures were designed accordingly. The concept of a 100-year flood, a flood with a 1% chance of occurring in any given year, entered the vocabulary of planners and engineers, providing a metric for acceptable risk. The San Diego and Arizona Railway was rebuilt, but its route was altered in sections where the original alignment had proven too vulnerable. Embankments were raised. Bridges were redesigned to withstand higher flows. The line reopened in 1919, 3 years after the flood, at a cost that exceeded the original construction budget. The experience influenced rail planning across the region. Future lines were routed with greater attention to flood risk, even when that meant higher construction costs. The reservoirs that survived the flood were modified. Sweetwater Dam was reinforced and its spillway enlarged. Morna Dam was evaluated and found to be structurally sound, but its capacity to handle extreme inflow was questioned. Barrett Dam, which had held during the flood but had come close to failure, was later replaced with a larger structure. The new Barrett Dam, completed in 1922, was designed with the 1916 flood as the reference event, the benchmark against which all future floods would be measured. The flood did not end development in Southern California's valleys, nor did it eliminate the risk of future disasters. What it ended was the assumption that the region's hydrology could be fully controlled with the engineering knowledge and infrastructure of the early 20th century. The dry channels that returned in the months after the flood were no longer seen as empty space waiting to be used. They were seen as pathways for water that would, eventually, return. The floods of 1916 had reshaped not just the landscape, but the relationship between Southern California and the water that defined it.